This is another question on diffraction grating. So let me write down the question first. So the question says, a beam of light is incident normally on a diffraction grating of width 1 centimeter. It is found that at 30 degrees the nth order diffraction maximum for lambda 1 equal to 600 angstroms is superimposed on the n plus 1th order for wavelength lambda 2 equal to 500 angstroms. How many lines per centimeter does the grating have? Find out whether the first order spectrum from such a grating can be used to resolve the wavelengths lambda 3 equal to 5800 angstroms and lambda 4 equal to 5802 angstroms. So this is the question on the diffraction grating and resolving power of the grating. So let us look at the first part. The condition for maximum is as follows. We have d sine theta equal to n lambda. This is the condition for maximum. D is the grating element, or it is equal to line width plus the width of the transparent part. So it is basically the separation between two consecutive slits. So let us look at the values given in the question. So we are given that d sine 30 degrees is n lambda 1 and d sine 30 degrees is also equal to n plus 1 but for wavelength 2. So if we take the ratio of this, then we get the following. So let us rearrange the terms. So this is the value of n we will get. Lambda we know is given to us. So this is 500, lambda 2 is 500 angstroms and lambda 1 is 600 angstroms. Sorry, this is 600 minus 500 because lambda 2 is 500 angstroms and lambda 1 is 600 angstroms. So this gives us the following. So we find out the value of n, but we need to find out the value of d, the grating element. So we can plug this value of n back into this equation. So we have d sine 30 degrees is equal to n lambda 1, but n is 5. So this is 5 times lambda 1, which is 5. So this is 5 times lambda 1 is 600 angstroms. This is a little bit artificial in the question. So typically for the wavelength of light, this should be 5000 angstroms and not 500, and this should be 6000 angstroms instead of 600. So if we can definitely solve the question in this manner, but it just feels pretty much artificial and unphysical. So just to make things more realistic, let us use more realistic value of wavelength for the incident light beam. So this wouldn't change the value of n, by the way, because this would just have extra factors of 10 out here, which would essentially cancel out, giving us the same value of n. But over here this will make a difference. So this is 5 into 6000 angstroms, and this is equal to 30,000 angstroms, which is equal to 3 into 10 to the power minus 6 meters, which happens to be equal to, if we write it in centimeters, into 10 to the power minus 4 centimeters. Now we need to find out the grating element, that is how many lines per centimeter does the grating have. So number of lines per centimeter for the grating is going to be width of grating divided by grating element, which is nothing but d. So width of the grating we are given is 1 centimeter, and this denominator is d, so it is 1 centimeter over 3 into 10 to the power minus 4 centimeter, which is roughly equal to 0.33 into 10 to the power 4. So this happens to be as follows. So this is the number of lines approximately in the grating. So this solves the first part. Next part is on resolving power. So in the previous video we saw the expression for resolving power, which is given as follows, where wavelength is average wavelength and delta lambda is the difference in the wavelength, and this is also given as follows for a grating with n number of lines being illuminated, and capital N the number of lines and small n the order of the diffraction spectrum. So let us find out the resolving power and solve this question. So resolving power of the grating is as follows, and we want to see, the question asks us whether it is possible to resolve in the first order spectrum. So for first order, n is equal to 1. So this simply reduces to the following, and this n we just found out in the first part is this 3333. And for the given set of wavelengths, resolving power is as follows. So lambda is this, and delta lambda the difference between wavelengths. So this comes out to be as follows. Let us put in the values. So this is the resolving power for the given combination of wavelengths, and this is the resolving power, maximum resolving power for the grating in the first order. So we clearly see from here, this is, let us say, R max for grating in the first order, and this is R for the given set of wavelengths. So clearly in our situation, we see that resolving power of the grating is much more than the required resolving power for the given set of wavelengths. So this means that we can resolve lambda 3 and lambda 4 of the given wavelength 5800 angstroms and 5802 angstroms. So lambda 3 is given to us as 5800 angstroms and lambda 4 is 5802 angstroms. So we can resolve lambda 3 and lambda 4 using the grating in the first order spectrum. So this solves the question on diffraction grating and resolving power. So takeaway from this question was that we can find out the resolving power of the grating and the resolving power for the given set of wavelengths, and then we can see whether we can use a given grating to resolve the wavelengths that we have.